CubeSat. So here we go. Here's our CubeSat, our Z, X, Y. What are CubeSats? CubeSats are nanosatellites. The normal dimensions are 10 centimeters times 10 centimeters times 11.35. Today, we're going to be demonstrating basics of CubeSat and how CubeSats work. And they're 10 centimeters times 10 centimeters times 11.35 centimeters, so that way the inside volume is 10 times 10 times 10. We are just going to use something more simplified today of 10 centimeters times 10 centimeters times 20 centimeters, because we're going to use a 2U CubeSat based off what the Oresat, or the Oregon collaboration. It's making nanosatellites between a bunch of universities across Oregon. We're going to be demonstrating what they're doing in the simplest forms. So we're just going to do 10 centimeters times 10 centimeters times 20 centimeters, make it clean, not have all these weird decimals and stuff, which we'll end up having anyways. So we're going to want to calculate the inertia of our CubeSat, our nanosatellite, and which is around each plane is Ix will equal 1/2 m y squared plus z squared. Iy will equal 1/2 m x squared plus z squared. Iz will equal 1/2 m x squared plus y squared. You do this by taking the integral, inertia formula, area, and you get these, and we calculate them out to be 0.029 kilogram meter squared, 0.29 kilogram meter squared, and 0.012 kilogram meter squared. The mass of our cube is 7 kilograms. We're just going to keep that very simple. The point of CubeSats are they're cheap, and you can send them to space for cheap because sending stuff to space is expensive. So it's just a cheap way to get something to space where you can go take data, do research, either put a telescope or something. So we're going to demonstrate the simplest, like the basics of what a CubeSat is. How do CubeSats move? So CubeSats use different things: thrusters, gyroscopes, reaction wheels. But the main way that most of them do is a reaction wheel. Now, what is a reaction wheel? Reaction wheels are the theory is that a reaction wheel controls the movement of the box through conservation of energy. So right, if you have something that's less tilted and you want to move some way, the wheel will just spin in the opposite direction, right? So the inertia of the box times the angular velocity of the box will equal inertia of the wheel times angular velocity of the wheel, right? So if you spin the wheel this way to the right, then where will the box spin? It will spin to the left. There's lots of good videos on YouTube to demonstrate this, like the one linked in our project. And so basically, yeah, they cancel out. So if you spin the wheel one way, you can get the whole entire system, the whole box, to spin the other way, and that way you can change it directionally. These are good because they don't require a lot of power, and it's a lot cheaper than using thrusters and sending with fuel, because you don't need to send fuel to space. So the CubeSat, so they're really powerful, and most CubeSats, they'll use 3 system reaction wheels, so 3 axes. You put one along your X, Y, Z. It's a cube, right? So we got 3 dimensions. They'll set it, and it's really often used for telescopes and cameras, which is a big reason why CubeSats exist in the first place. So we're going to design one. We have some constraints. It must fit within our cube, our rectangular prism. We're going to try and minimize the mass, right? Because we're sending something to space. We want it to be light. And we're going to must have big moments of inertia. Radius. So our radius of our wheel will be 5 centimeters. Our mass, 85 kilograms. We're going to use an aluminum composite. This is most commonly used in spacecraft. So they're strong, it's cheap, it's light. It's light. We found the mass 2 pi times the mass per grams. We got 85 grams. The shape of our wheel is. So I just try to use a hollow wheel, right? So imagine like this is the wheel. So essentially we're cutting out half of the mass of the wheel. Let's say if both of these were made by the same aluminum composite, right? But this will be 2 times the mass because it's full. This isn't, because we're taking out half of the mass of this wheel. We're going to say these little spokes, their mass is negligible. There's be some slight error on our overall our end results. But right, say a full like a circle. If our disc was full and we're using the same material, it'll be double the mass. We're gonna cut out a circle so this is half the mass, and that way the inertias are the exact same, but our mass is lighter here. So because if this mass was double, right, 1/2 mass, and this is mass r squared, 1/2 the mass, those would be equal to each other, right? So essentially, these inertias, these shapes are equal to each other, but this mass is going to be less. And we want it to be light, so we're going to have our reaction wheel be hollow, if you can picture that. And suppose we want to rotate our satellite from rest by 90 degrees in 45 seconds and come back to rest. Assumingly, Oresat, we're going to put the Oresat on a 0, 0, 0. We're going to rotate it around the YZ axis because we're moving it by 90 degrees around the x-axis. So we're putting it along the YZ axis. What is our angular acceleration? We're just going to use our rotational kinematics using our change in radians is equal, this isn't clear, equal to 1/2 angular acceleration t squared plus angular velocity times t, right? Our omega is just crossed out, so 1/2 alpha t squared is equal to change in radians. We know it's 90 degrees, so pi over 2 equal to 45 seconds squared, 1/2. So 1/2s cancel. So our pi is equal to our alpha, 45 squared. Solves out to be 0.0015 radians per second squared. That should be squared. Okay, so now we want to find our omega, our W, and we're going to do this by, right, we have 45 seconds it's going to spin for. We want it to go to 90 degrees in 45 seconds. If it spins for 45 seconds until peak and then stops, it's going to keep moving after 45, right? Because if it keeps moving, there has to be a change. As long as there's any angular velocity, because remember the equation of conservation of momentum is inertia times angular velocity times that omega. So as long as there's any then the inertia is going to spin for the box, as long as it has to be 0 for our angular momentum to be 0 of the wheel, so that way our box is 0, because they'll always be equal to each other, at least that's the theory. So we're going to have it go up proportionally and go down proportionally, the speed up proportionally, go down proportionally, decelerate proportionally. And the area will be pi 2, because that's the change in radians, 45 seconds. So we can just do that, the area of a triangle, pi 2 equals 1/2 base times height, 45 seconds times height, which we get is 0.064 omega. And then we want to find what is the maximum power needed. So we're going to use the power is the torque, power is equal to torque times angular velocity. And remember, torque is going to be inertia times alpha, angular acceleration. So inertia of the wheel times angular acceleration times alpha times omega, we're going to be equal to 2.0002 watts. I did this with the inertia of the box, but the wheel is what's being powered, not the box is being powered. So yep, that's essentially how much power is going to be needed.